was investigating the effects of 3D print orientation and infill percentage on fracture strength of 3D printed parts. We're Team 20. My name is Jack.
My name is Tim.
My name is Caden.
My name's Zach.
I'm Ava.
Alright, so how we did it, we printed samples either vertically, horizontally, or diagonally at 45 degrees, each at different infill percentages, 5, 10, or 15%, to determine if there was a statistically significant interaction between the infill percentage and orientation at which the sample was printed.
So why we perform this experiment? As engineers, an experiment like this is a pretty important one to do. Our main considerations when we're printing is time and money. We want to reduce print time, and we want to decrease the amount of filament that we are using. So if we prove that there's no statistically significant difference between our infill percentage or orientation, then we would want to pick the one that minimizes the print time and minimizes the filament used. So that is generally why we're performing this experiment. If we're looking at the cause and effect diagram, we can see all the different things that may have an effect on the final print. So we're going to do the print production. We have the print settings, which we'll go over in a little bit, the quality consistency of the prints. Under the actual samples, these are things that we were changing as the orientation and infill, and then of course the accuracy of the actual print, what the model predicts is going to happen, and then what actually happens. And then we have the testing. We have an informal procedure for how we were testing. Again, we'll go over that in a little bit, and then the equipment that is going to be used.
In terms of the experimental design and the statistical analysis performed, we just did some general sample group tests, median, mean, identifying outliners, and then we did a confidence interval and a one-way and two-way ANOVA test, one for the hypothesis test and one for the interaction test. For the response variables and hypotheses testing, our response variable was the fracture force and the predictor variable were the print settings, most generally just the orientation and that info. We have our null hypothesis, which is that there is no association between those two print settings and the applied loading at fracture, and then the alternative hypothesis, which is that there is an association between those print settings. And then for actually performing the experiment, we printed some rectangular samples of dimensions 5 by 1 by 0.2 inches that were printed out of PLA on a FlashForge Adventure 3 Pro printer. These samples were placed between two flat surfaces, and a point load was applied to the center of the sample and measured using a force sensor. The force was applied until each sample completely broke, and the maximum force that each sample was subjected to was recorded.
Okay, like Ava was saying, we printed 9 different variations of identical parts with 3 repetitions each, which made a total of 27 total parts tested. We printed with 3 infill types, 5, 10, and 15%, and 3 angles of print, horizontal, vertical, and diagonal, which are pictured to the right here. The top right is horizontal, the one on the left is the vertical, and the one on the bottom with supports is the 45-degree angle. And for each part, we attached a force sensor to the testing apparatus and performed a 3-point bending test and recorded the maximum value that each sample was able to take before breaking. Our print settings were kept consistent throughout the experiment using PLA filament and these bed temperatures, nozzle temperatures, and print speeds, and our infill geometry was kept as hexagonal. And here are some images from our experiment. On the left is one of our prototype prints after it broke with a 5% infill, and the image and video on the right showcase our testing procedure with measuring the load. And now our raw data, we basically just recorded each fracture strength and tabulated it in Excel and averaged all of the repetitions as well as the average for each orientation and infill percentage. And then the bar graph on the right is a little bit better visual representation of each sample and where they each broke at. If you can, just based on the bar graph, it's pretty easy to tell that our orientation, the horizontal orientation, has the highest strength out of all of them, and going down as we go across.
So the first thing we did in terms of data analysis was to conduct confidence intervals. We conducted 90, 95%, and 99% confidence intervals, the 3 standard intervals, just to kind of get a rough estimate as to where our sample means were at using the built-in MATLAB t-test command. It's a function, one of the outputs of that function is actually the confidence interval. So using the code provided in the top left of the screen, we were able to just conduct all of the confidence intervals. I've only included 2 of the columns of confidence intervals on here because it was pointless to include all of the 3 data tables. That's just pointless repetition. But as you can see, that's the 90% confidence interval in the top right corner there. And then we conducted a one-way ANOVA test for difference in sample means as per the syntax from the book. The null hypothesis was that all sample means are the same. The important thing when entering the data into the ANOVA command in MATLAB is that you need to have a column vector and corresponding categorical data for each entry. That's the ANOVA table that was produced. As you can see, a very high F value corresponds to an extremely low probability value of about 1.6 times 10 to the minus 5. Using that previously constructed one-way ANOVA table, we ran a multi-comparison test using the built-in mult-compare MATLAB syntax, and we were actually able to get a graph depicting which of the sample means were different in a statistically significant manner from the other ones. As you can see from the figure in the bottom right corner, group 2 had the highest sample mean, while groups 1, 3, and 4 had similar sample means that were not statistically significantly different from that mean. We also conducted a two-way ANOVA test to determine which factors were significant. Again, you need to have a column vector inputted into the ANOVA table with categorical entries corresponding. The only difference is for the two-way ANOVA test, you need to have 2 categorical variables for each entry. Upon generating the ANOVA table here, we can see that the orientation has an extremely high F value of approximately 39.3, with a corresponding probability so low that MATLAB rounded it to 0. So therefore, that would be significant at any significance level. Same with percent infill. Same with the interaction effect between the orientation and percent infill. However, the percent infill by itself had an F value of 0.19, which would be rejected at any of the significance levels. Again, we generated one final figure depicting the group means as related to the vertical, horizontal, and 45-degree orientations. Again, this depicts something similar to the bar graph a couple slides prior that shows the horizontal orientation as the mean that is highest in a statistically significant manner, which leads to the following conjectures. Pretty clearly, we can see that the null hypothesis should be rejected. We have a very high value of our F statistic that would be rejected at any significance level, which means that at least one of the 9 sample means differs from the others by a statistically significant amount. So from this, we can include that orientation and or the infill layer, so just the print settings in general, have some effect on the breaking strength. And here's the most important part of our analysis is actually determined that the horizontal 5, horizontal 10, horizontal 15, and vertical 5% don't vary from one another in an amount that's statistically significant. These are the 4 greatest mean values. So what we want to do is we want to take a look at the print time as well as the material usage. As engineers, a lot of the time we always have the material that we need, but not necessarily the time. So we can see that 8.23, 8.84, 9.65, and 11 grams of filament are, they're close enough. What we want to do is pick the lowest number there. But for the print time, we have, between 51 minutes and 70 minutes for the print time. What we want to do is pick the combination of the lowest amount of filament used as well as the lowest print time. So with those 2 combinations, we conclude that the horizontal orientation with a 10% infill layer would be the best combination to save on both filament and time.
Some obstacles we ran into while performing this experiment was properly calibrating our 3D printer to very consistently print test samples, as well as any print time. To print close to 30 samples, it required upwards of 30 hours of printing time, so scheduling that in with our already busy class schedules was another obstacle. And then we also redesigned our test sample to optimize for print time and also changed our material from PETG to PLA. In the future, we would like to either establish a more precise definition of a break for more accurate force measurements, or specify what type of fracture is present for each measurement to help determine which samples could be used for certain applications. And this is just because each orientation broke in a different way. And those different kinds of breaks could signify different use cases for different print orientations.
A source of error that we encountered during our project was from the force sensor. The force sensor the force sensor likely introduced small errors because it was one of the cheapest and therefore least accurate options available. To determine the braking force, a video was recorded of the sensor as force was applied. The braking force was later obtained by reviewing the video footage. A more elegant or precise measurement method would have been preferable, but budget limitations made this approach necessary. The 3D printer also had some sources of error from the 45-degree orientation, requiring lots of supports, which would have produced more defects in the print. The testing apparatus. The test section was not clamped to reduce movement. Once this force was applied, the test section slightly slid. This added non-even force distribution and force being applied in a non-vertical direction.
Any questions? Thank you.